Okay. Welcome everyone to the 11th webinar of our BNP section. We hope you had a peaceful and restful break. And today's talk will be the first one in the second year of our webinar series. And I would like to thank you for attending this seminar at this particular time. Today, I have the great pleasure of introducing Professor Yongdai Kim as our speaker. Dr. Kim is a professor in the Department of Statistics at Seoul National University in South Korea. His research interests include survival analysis, Bayesian statistics, statistical learning and data mining, model selection, and big data analysis. The title of his talk today is Adaptive Bayesian Inference for High-Dimensional Sparse Factor Models. Please recall that you can ask clarification questions during the presentation. However, we ask you to hold all non-clarification questions until the end of the presentation. So, Dr. Kim, thank you for accepting this invitation. And without further ado, please join me in welcoming Dr. Kim.
Okay, thank you, Andres. Thank you for a nice introduction. And I thank everyone for coming to my talk. The title of my talk is Adaptive Bayesian Inference for High-Dimensional Sparse Factor Models. And this is a joint work with my former PhD student, Il Sang-won and Lee Jen-min. Actually, Il Sang-won is currently a postdoc of Lee Jen. The outline of my talk consists of introduction and review of other inference methods and our proposed prior and MCMC algorithm and asymptotic properties of the posterior distribution, numerical studies, and discussions. Actually, these two parts is a main part of my talk, and basically I'm going to propose a new Bayesian models for high-dimensional sparse linear factor models, which has nice asymptotic properties. Okay, let me go to the introduction. Okay, this is a linear factor model. I assume that you are familiar with these linear factor models. We have two random vector. Y is a p-dimensional vector and z is r-dimensional vector, and conditional distribution of y given z is p-dimensional Gaussian distribution. Is mean is p times z and the variance is psi I, and marginal distribution of z is r-dimensional normal distribution with mean 0 and the variance identity matrix. Here the matrix B is called the factor loading matrix, which is a p times r dimensional matrix, and we call R is a factor dimensionality. And Z is the latent factors. And under this model, the marginal distribution of Y is given by the p-dimensional Gaussian distribution is mean 0, and sigma is given by BB transpose plus psi I. This is our well-known result. And in this talk, I consider a high-dimensional linear factor model, which is simply a linear factor model, but P is much larger than N. And we are going to estimate the true factor loading matrix. And since P is much larger than N, at least we have two problems. One is number of parameters would be too large compared to the sample size. And the second problem is that the factor dimensionality R is usually unknown. And for these problems, there are popular remedies. First, for large P, we assume that true factor loading is sparse. And I will explain what the sparsity of the factor loading matrix is. And then for unknown factor dimensionality R, we estimate the R as well as the factor loading matrix. Let me explain what the sparsity of the factor loading matrix is. There are two versions of the sparsity of the factor loading matrix. The first one is row-wise sparsity, which means that there are p many rows in the B star, and among the P many low vectors, only S many low vectors are non-zero vectors. In the case, we say that B star is the low-wise sparsity with the sparsity level S. Now, the definition of sparsity is column-wise sparsity, where each column vector of B star has at most as many non-zero entries. These two versions of sparsity are different, but if R is bounded, then the two sparsities are similar, at least asymptotically, which means that low-wise sparsity is has the same order of the column-wise sparsity, because the S column-wise sparsity implies that S times R low-wise sparsity. So if R is bounded, the column-wise level of column-wise sparsity and the level of low-wise sparsity have the same orders when S diverges. And this is the aim of my talk. In this talk, I propose a prior on the factor loading matrix, which is P times infinity matrix, since we do not know the factor dimensionality R. But our prior has many desirable properties, such as, first of all, its computation is easy. And second one, which is the main part of my talk, is that the tau B, which is the non-zero column vectors of B, so it's an estimation of the factor dimensionality, and we show the posterior distribution of the factor dimensionality is consistent. But there are two features. First one is that our prior does not use the true sparsity. So we say that our prior is adaptive to the true sparsity levels. And second, desirable property is that our posterior is consistent with the optimal detection rate. Here, the detection rate means the size of the smallest eigenvalue of the B times B star transpose. I will explain more details about this optimal detection rate. Furthermore, the posterior contraction rate of the covariant matrix is also almost the minimax optimal. But and in this talk, I assume that true factor loading matrix is low-wise sparse. Okay, let me review some other Bayesian models as well as corresponding frequentist estimators. There are some priors on P times infinity loading matrix. Two of them are Bhattacharya and Dunson and Srivastava et al. In 2017. And this is a kind of shrinkage parameters. So beta JK for larger K are more shrunken to 0. But there are no theoretical results about these priors. And many priors are proposed which put prior mass on the factor dimensionality directly. And Patti et al. In 2014, they proposed two priors. One is spike slab with Poisson, and the other is Dirichlet Laplace with Poisson. In this prior, they use Poisson distribution for the prior of the factor dimensionality, and for given factor dimensionality, they use the sparse priors. First one is spike slab prior, and second one is Dirichlet Laplace priors. So they have sparsity, and also they have priors on the factor dimensionality. And they also prove some theoretical result. In particular, they drive the posterior contraction rate when the true factor loading matrix is column-wise sparse. And there, the posterior contraction rate is minimax optimal when R is bounded. but they do not study about the posterior distribution of the factor dimensionality, and I don't think it is consistent. The second prior, which put prior mass on the factor dimensionality directly, is Lakova and George in 2016, where they used the Indian buffet process for the prior of factor dimensionality, and they use this kind of slab and spike priors for the sparsity of the factor loadings. And they derive some this kind of convergence result, which means that the posterior distribution of factor dimensionality is not large, but they do not show the posterior consistency of the factor dimensionality. They also assume the columnized sparsity. And recently, Il-Sang-won and myself studied and proposed a prior, which is an extension of the prior of Lakova and George, where instead of Indian buffet process, we use two-parameter Indian buffet process prior for the factor dimensionality. So this is a two-parameter Indian buffet processes. And reason why we use the two-parameter Indian buffet process prior is that we want to have the posterior consistency of factor dimensionality. And we derive the posterior contraction rate, and we can prove that the posterior consistency of the factor dimensionality. So we are happy, but we have still problems. The prior depends on the sparsity level S. If you look at here, this beta distributed part, there is S squared, which means that this prior is not adaptive to the sparsity level. So today I'm going to propose a new prior which is adaptive to the true sparsity, which is the main theme of my talk. And there is another prior which put prior mass on the only orthogonal factor loading matrix, which is proposed by Gao and Zhu in 2015. They developed very interesting but complicated priors, which only put the mass on the orthogonal factor loading matrix. And they proved that the posterior distribution has nice asymptotic properties, such as fast contraction rate and posterior consistency of factor dimensionality. But the problem of this prior is that here, posterior computation is almost impossible for me, because orthogonality constraint makes the MCMC algorithm is really difficult. So I don't think it's practically useful one. But the Bayesian model we proposed this talk is computationally much easier. And there is recently Bayesian models for row-wise sparsities also, and we found two results about the Bayesian factor models with row-wise sparsities, and they drive the fast convergence rate. But the problem is that this research assume that the true factor dimensionality is known, so they only focus on the estimation of sparsity. But we are considering the problem of estimating the factor dimensionality. And there is also the frequency estimators, and Kai and his colleague wrote two papers. In 2013, they proposed a consistent estimator for the factor dimensionality, but the detection rate is larger than the optimal one. So it's not the optimal. Is also the noise variance psi is assumed to be known. And 2 years later, they also wrote another paper and they proposed another estimator for factor dimensionality R. And also they proved that the covariance estimator is minimax optimal. And in this paper, the detection rate for the consistent estimate of factor dimensionality is optimal. So it's good. But the problem is that the sparsity level should be known in advance. That means that inside the estimator, the sparsity level S is used. So which means that the estimator is not adaptive to the sparsity levels. Also, they assume the noise level psi is known. So this is a record of the aims of my talk, that we propose priors such that computation is easy and the posterior distribution of factor dimensionality consistent, and which is adaptive to the sparsity level S, and also it is consistent under the optimal detection rate. And also the posterior contraction rate of sigma is minimax optimal. So we propose a Bayesian model, which is computationally easy and has a nice theoretical properties. Okay, so now it's time to explain the Bayesian models. Let me show the priors. First, we choose the Rmax, which is the very large integer such that the true factor dimensionality is much smaller than these large integers. And choice of this integer is not important because this integer does not affect any theoretical properties. So it's a computational. Actually, we choose Rmax like 100 something, and we need two binary vectors, p-dimensional binary vector and the Rmax dimensional binary vectors, and we allow that factor loadings can be non-zero only when uj times vk is 1. So binary vector u represent the non-zero low locations of non-zero low vectors. So it's a vector loading matrix, and this is low locations of non-zero low vectors, and V is the location of non-zero columns. Then we have submatrix, whose entries are non-zero, and the element entries of the vector loading matrix are 0. So U is a position of non-zero low vectors, and V is a position of the non-zero columns. So basically, L0 norm of V is factor dimensionality. And we propose following prior, which is specialized, invented to make the posterior distribution have nice asymptotic properties. One interesting feature of this prior is that it only depends on the number of non-zero low vectors and number of non-zero column vectors, but they are not independent. So the prior depends on the S times R, S prime times R primes. So that means it depends on the product of non-zero low vectors and non-zero column vectors. Initially, we tried to use the independent priors for the non-zero low vectors and non-zero column vectors, but the posterior distribution doesn't have nice frequency properties, so we devised these priors. And there are some terms, this is a normalized terms. And conditional on U and V, everything is straightforward. Conditional on U and V, we use a slab and spike priors for the factor loading, each factor loading, where the spike part, slab part, we use a Laplacian distribution. And prior for the noise variance, we use inverse gamma distribution. And I'll briefly explain the MCMC algorithm, and which is very simple. MCMC algorithm, we first sample the factor loading from the normal distribution or the zero. And the parameters in the normal distribution is easy to calculate. And also we sample the auxiliary parameter tau jk, which is used to decompose the Laplace distribution as a mixture of normal distribution and exponential distribution. And this is auxiliary parameters for that purpose. And the conditional posterior distribution has a following closed form solution. And for mu j, we generate it from the Bernoulli distribution with the success probability given by following equations, which is easy to calculate. Similarly, also we sample the Vj from the Bernoulli distributions with success probability, this form. So it's easy to calculate. And also we can sample the latent vector Zi from the normal, either of these two normal distributions. And it's easy. And finally, we sample the noise variance psi from the inverse gamma distribution. That is all the MCMC algorithms. So, and we repeat this, the sampling of conditional posterior distribution until convergence. There is no spatial algorithm for sampling. So it's very straightforward and easy to implement. But the posterior distribution has nice asymptotic properties. Okay, let me first introduce some notations. For given factor loading matrix, we define low-wise support as a set, the set of the low vectors which are not zero vectors. And we say that the loading matrix B is S-sparse if the cardinality of support of B is less than or equal to S. And BPRS is a set of loading matrix which are P times R matrix, and its sparsity is less than or equal to S. Then we consider this parameter space where we expect that true covariance matrix belong to. Okay, let me explain that, some details. Sigma, the covariance matrix is B transpose times psi r. This is a linear vector matrix. And the vector loading matrix belongs to this BPRS. Then that means that the sparsity level of the vector loading matrix is less than or equal to S. And the largest eigenvalue covariance matrix is less than or equal to lambda. And the noise variance is lower bounded by psi 0. And there is some conditions on the minimum eigenvalue and the L2 norm of the non-zero low vectors. And first of all, the minimum eigenvalue of the vector loading matrix is greater than zeta, and also the L2 norm of the non-zero low vector is greater than zeta. That is the parameter space we consider, and we study the asymptotic properties of the posterior distribution when the true covariance matrix belongs to this parameter space. This is remarks about the choice of parameter space. Posterior contraction rate of the covariance matrix depends only on the dimension P, sparsity level S, and factor dimension R, and the upper bound of the largest eigenvalue lambda. And the conditions for the lower bound of the noise variance and the lower bound of the smallest eigenvalue, they are only needed for the consistency of the factor dimensionality. In particularly, lower bound of noise variance is introduced to avoid the ill-conditioned covariance matrix, and conditions of the smallest eigenvalue is lower bounded by zeta, is the eigengap between spikes and nodes, which prevents the underestimation of factor dimensionality. Also, the last condition, the L2 norm of the non-zero low vector is low bounded by zeta, is similar to the so-called beta mean condition for high-dimensional linear regression models. So, I mean, all the conditions are very general ones and natural ones. This is the first, the theoretical result, which is the posterior consistency of factor dimensionality. So let epsilon is lambda times square root of SR log P divided by N. And for some lambda is less than or equal to S. Lambda is the largest eigenvalue of the covariance matrix. And assume that this epsilon is literal 1, and the zeta, this is low bound of the smallest eigenvalue, is greater than or equal to the epsilon. And assume that the true factor dimensionality is smaller than log P divided by log N, which means that R is not too large. In that case, we proved that for all the true covariance matrix belong to the parameter space we considered, the posterior distribution of factor dimensionality is consistent. That is the first main result. And there are some remarks. In Gao and Zhou, who consider the orthogonal factor loading matrix, they assume that R is less than or equal to log P. So our condition, which R is less than or log P divided by log N, is slightly stronger than the condition of Gao and Zhou, but recall that we do not use any orthogonality constraint, which makes computation is very difficult. And here the detection rate, this zeta is called the detection rate. So eigengap. And the lower bound of our detection rate is smaller than the detection rate of Chi 2013, where the detection rate of Chi is square root S times larger than the ours. Smaller the detection rate, the better we have. And in the estimate of Chi in 2015, that estimate is consistent under the minimum detection rate, same as ours. But as I mentioned earlier, the estimators of Chi's 2015 is not adaptive to S. But our Bayesian model is adaptive to S. We do not use any information about true sparsity in the prior or the model. And our detection rate, this one is the lower bound of the detection rate. And we can prove that this detection rate is optimal, which means that if the smallest eigenvalue is less than the lower bound of detection rate, then we have the posterior distribution of the estimated factor dimensionality is not equal to R. True factor dimensionality is greater than some numbers. So this is optimal detection rate, and this is lower bound of the detection rate. So this is optimal detection rate, and similar optimal detection rate is derived by chi, but in chi there is no lambda. That means they only consider the bounded lambda or even divergent lambda, but their low bound is s log p divided by s divided by n. So there is a lambda. So the low bound is better than the chi's low bound in that sense. And the second result is posterior contraction rate of the covariance matrix, and we derive this posterior contraction rate, and this contraction rate has many desirable results. Let me summarize that. So when R is bounded, then our posterior contraction rate is minimax optimal, and the lower bound is derived by Patti et al. In 2014. Also, our posterior contraction rate is similar to or better than the existing frequentist estimators. For frequentist estimators, the chi's estimators, they assume that the noise variance is known, but we do not assume that noise variance is known. So our model is bigger, but we have the same contraction rate. So in that means our contraction rate is better than the frequentist estimator. Okay, let me briefly show the result of numerical studies. I did very simple simulation experiment. So when for given P and R, so then for given P, we select the as many low vectors randomly out of P low vectors. And then for selecting non-zero low vectors, we generate the vector loadings from -2 or 2 randomly. And we let the true noise variance is 2. And then we vary the true sparsity and vector dimensionality such that the true sparsity is either 10 or 15, and the true vector dimensionality is either 1 or 5. And we compare the Bayesian models with 5 frequentist estimators of vector dimensionality. One is ET and ER. There are many, GR, HT, and DT. And all these methods are similar in the sense that they estimate vector dimensionality by first calculating the eigenvalues of the estimated variance covariance matrix and then thresholding small eigenvalues. And this is the simulation result. These are the 5 frequentist estimators, and this is our Bayesian models. And true means that the estimate dimensionality is exactly equal to the true dimensionality. Now, over means that the estimate vector dimensionality is larger than the true vector dimensionality, and under means that the estimate dimensionality is less than the true dimensionality. And for when the true dimensionality is 1, it's very small, then our method works well, but our method perfectly identify the vector dimensionality. But the true vector dimensionality becomes larger than the other. The frequentist estimators have serious problems. They are all underestimate. And for even for the largest sparsity, they do not work well. But compared to the other frequentist estimators, our Bayesian models works much better. Even for the R equal 5 and S is 50, they identified true factor dimensionality 91 times out of 100 simulations, where this estimator totally failed to identify the true factor dimensionality. And mostly the frequency estimator tends to underestimate the factor dimensionality. So it is good. And also we compare the estimation of covariance matrix. And for this experiment, we consider 3 competitors. One is Poit, proposed by Fan et al. This is a method not specialized for the sparse factor measures. This Poit is a method for non-sparse factor measures. But in the case, P is cannot be larger than N. And SPCA-VI is a Bayesian model proposed at Ning, and so which can be compared to our method. But this Bayesian model assumes that true factor dimensionality is known, and they only focus on the identifying the sparsity of the factor loading, sparsity pattern of the factor loading matrix. And MGPS is the Bayesian model which put prior mass directly on the P times infinity metric, factor loading matrix proposed by Bhattacharya and Dunson. And this is a mean scale errors. For the loss function, I use the operating norm. Not Frobenius norm. I use operating norm. And our Bayesian models works much better than the others. And sometimes the SPCA-VI is outperform the models, but it's unfair because SPCA-VI requires to know the true factor dimensionality, and in that case we use a true R. But in our model, we estimate this factor dimensionality, so sometimes our Bayesian model is inferior to the SPCA-VI, but I think this is because they use true R, that we use estimate R. And that is almost all from all my talk. And so let me finish my talk with some discussions. So first, it's a summary. So I propose a Bayesian model which is computationally easy. MCMC algorithm is very, very easily implementable. And also the posterior consistency of factor dimensionality is achieved with minimal conditions. In particularly, the detection rate achieve the low bound. So we have the optimal detection rate. Also, the posterior contraction rate of covariance matrix is fast. And actually, there's a bit difference between row-wise sparsity and column-wise sparsity. In our model, each signal law, each non-zero law vector is completely non-sparse. But column-wise sparse matrix, each non-zero column may have the sparse patterns. So somebody complained about these practical problems about low-wise sparsity, but we find out that we can modify our prior such that for each non-zero low vectors, we can make that non-zero low vector sparse. But we found out that such a modification does not affect the asymptotic properties. So I didn't present that prior in this talk. And there is unsolved problems. So one of them is the adaptive priors for column-wise sparsity when the our true factor dimensionality is diverging. Actually, we consider low-wise sparsity because we can derive some nice theoretical properties about the posterior distributions, but our techniques cannot be applied to column-wise sparsity directly. And we tried, but we failed. So that we leave this unsolved problem as a future work. And there's one future work we are going to work now is that we find one problem in the sparse vector models. Okay, this is a vector loadings. This is a P times R, and only as many rows are non-zero. That means P minus X variables are simply noise. They do not depend on Z, so they only the noise variables. We think that this is somehow unlikely the assumptions in practice. So we think we need some way of estimating non-sparse loading matrix for the high-dimensional linear vector models. And for high-dimensional models, there are too many number of parameters. So we used, in this talk, I used the sparsity to reduce the number of parameters. But so to estimate the non-sparse loading matrix, we need the row dimensional structures other than sparsity, and we are developing this new way of reducing the number of parameters, and we will present it somewhere else soon. And I think that is all for my talk, and thank you very much.
Okay, let's thank Dr. Kim for his presentation. This one. So we have enough time for questions or comments. So if you have any, please turn on your mic and go ahead.
Yeah, I have a question. It's Ed George.
Hi.
Very nice talk. I just wonder, Yongdai, there didn't seem to be any mention of rotations at all. Do you use rotations in your MCMC? Somehow you didn't talk about that, or do you just avoid rotations altogether?
That's a good question. Actually, we do not consider rotations, but actually we devise one point. Actually, the vector loading matrix is not uniquely defined. That's Ed mentioned. And but I'm not sure. But if it is possible that if we assume the sparsity, then the sparse vector loading may be unique. But I do not investigate that the uniqueness deeply. But even in our the priors, actually the V is not uniquely defined because it's a sparsity of column vectors. But if the permutation of column vectors has the same distribution.
Okay.
But actually we decide to use this unidentifiable model because we found out that MCM's algorithm seems to converge faster than using the non-permutable identifiable sparse matrix. Yeah, but we do not consider the rotations.
Why would
Thank
it converge more rapidly?
I don't know, but actually, it's similar phenomena is observed in EM algorithms. If you extend the parameter space, then the algorithm may converge faster. So maybe, but I look at more closely. Actually, we recently find this phenomena. So
Thank you.
Any other question, comments? Well, if not, let's thank Dr. Kim again for his presentation.
okay, thank you very much. Thank you, everyone, and